Hello students. Today's class we will see about basic blocks and flow graphs. You know very well that we are in the fourth unit and the input for this will be the 3 address code. So basically when we have the 3 address code, if our program is going to have thousands of lines, it is going to be very difficult to convert it to code. So the code generation is the last phase. So when we have the 3 address code as a whole chunk, it will be difficult. So in order to facilitate it, we are going to divide the 3 address code as blocks. Or in other words, we are going to segregate them as basic blocks, and we are going to show the flow between the blocks by means of a flow graph. So this way it will be easier for us to convert the entire 3 address code into proper target code. So first we will see about basic blocks. Basic blocks are nothing but a sequence of consecutive 3 address statements, and the control will enter in the beginning of the block and it will leave at the end of the block. So there is no halt or branch except at the end of the block. We'll see an example, then we will understand better. So in order to create such basic blocks, we are going to use an algorithm called as basic block partitioning algorithm. Any algorithm will have an input and an output, and there will be steps in the algorithm. So here also we have input as a sequence of 3 address statements or the 3 address code, and the output will be a list of basic blocks with each statement in exactly one block. So a single statement cannot appear in more than one block. And we have only 2 steps in the algorithm. First step is to determine the set of leaders. And in order to determine the set of leaders, we have 3 different criteria. The first criteria is the first statement of the sequence of the 3 address code is a leader. And then any target of a goto statement. In the 3 address code, there will be goto statements. So whether it is conditional or unconditional goto, the target of the goto statement will also be a leader. And the third criteria is any statement immediately following a goto statement, again whether it is conditional or unconditional, will be a leader. So these are the 3 criteria with which we determine the set of leaders for the given sequence of 3 address statements. In the second step, for each leader, its basic block consists of the leader and all statements up to but not including the next leader or the end of the program. So we are going to take the leader and then follow down till we reach the next leader. So you'll see an example, then we'll understand better. So here is a sample code given. This is the code given for a 10 by 10 matrix of an identity matrix. You can see here the diagonal elements are 1 and all other elements are 0. So it is a identity matrix. If the diagonal elements are 1 and all other elements are 0, it is an identity matrix. So if the problem is given, then we have to write down the 3 address code. So here we are given the 3 address code also. So these 5 lines of code is converted as 17 lines of 3 address code. So for the exam also, either the code will be given. If the code is alone given, you have to write the 3 address statement. And this is a part C question. So If the 3-address code is given, you can straight away start converting it to basic blocks. And as I have already told you, you have to explain about basic blocks. What is the basic block partitioning algorithm? And then you proceed with solving the problem. Okay, so we are going to apply the algorithm to these 17 statements. So as you can see, what is the first step? Step 1 is to determine the leaders. So as you can see in this code, the very first criteria is the first statement of the 3-address code is a leader. So that way, statement number 1, these are all the statement numbers 1 to 17. So 1 will be a leader. And then the second criteria states that the target of the goto statement is a leader. So we have 3 goto statements, the target being 2, 3 and 13. So all these 3 will be leaders. And then we have to consider the third criteria. The third criteria states that the statement immediately following the goto statement. So that is statement number 10 and statement number 12. For this goto, there is no statement. So totally we have 6 leaders. Statement number 1, statement number 2, 3, and then 10, 12 and 13. Let's see it little in detail. So as I told you, according to the given algorithm, instruction 1, that is the first statement, is a leader. And then instruction 2 is also a leader because this instruction is the target of the goto statement in 11. Similarly, instruction 3 is also a leader because this instruction is the target of the instruction 9, that is the goto statement. Then instruction 10 is also a leader because it immediately follows the conditional goto here. Then similarly, step 4, instruction 12 is also a leader because it follows this goto statement. And finally, instruction 13 is also a leader because this instruction is the target for instruction 17, which is a goto statement. So we have to apply the 3 criteria given on the given 3-address statements, and thereby we are able to obtain the leaders. So totally there are 6 leaders. So that many number of blocks we will have. So there are 6 basic blocks for the above code. So for each leader, we will assign a block. So for statement number 1, B1, statement number 2 is a leader, so it is B2. And statement number 3 to 9, because as per step 2, from the leader, we have to go down till the next leader. See, if I take B1, there is only one statement because statement 2 itself is a leader. So that is why in B1 there is only one statement. Similarly, in B2 also we have statement number 2. Immediately 3 is the leader. So we have to assign only statement number 2 to B2. Whereas in 3, statement number 3 is the leader, but we can go up to the next leader. Next leader is 10. So till 10, before 10. So 3 to 9 will be B3. And B4, next leader is 10. The very next leader is 12. So 10, 11, they will be B4. Then 13 is itself a leader. So 12 alone will be in B5. And 13 up to the end will form B6. So carefully analyze, we are just applying step 2. So from the leader till the next leader. So that is the case. We have to carefully see the leaders. So 1 is a leader, 2, 3, 10, 12 and 13. So whichever statement is before that will be considered as a leader. So with this understanding, you can separate the blocks. And once I separate the blocks, I can draw the flow graph. So flow graph is nothing but a directed graph. So after partitioning an intermediate code into basic blocks, the flow of control among the basic blocks is represented by a flow graph. So an edge can flow from block X to another block Y in such a case when Y block's first instruction immediately follows the X block's last instruction. So what is an edge? So there is a conditional and unconditional jump from the end of X to the starting of Y. And Y will immediately follow X in the original order of the 3-address code. So we will check with the example for us and then we will understand this. So once you draw the blocks, then you have to proceed with drawing the flow graph. So the question can be asked either with both flow basic block and the flow graph, or it could be asked separately as basic block, separately as flow graph. So either way you have to explain the theory and proceed. So you can see here, as I told you, we have the 6 blocks. So we will always have an entry block and an exit block added. And we have V1 with only one statement, V2 has only one statement, as we already discussed. And instead of the label, we have changed it to the block name. So we told go to 2. Instead of that, we are putting this block number itself. Go to 2, go to 3, and here it is go to 13. So that is nothing but block 6. So B1 is the entry point for the flow graph because B1 contains the starting instruction. Then B2 is the successive of B1 because B1 does not end with unconditional jump. Then B2's block leader immediately follows. All this we already discussed. So that is how we have drawn the blocks. Now we are just connecting the blocks by the flow of the program, and that becomes our flow graph. Here is one more example. We are given the 3-address code consisting of 11 statements. So once again we can apply the rule. So we can find out the leaders. So the very first statement is a leader. So statement 1 is a leader. And then the target of go to is a leader, which is 5. So 5 is again a leader. And the third criteria is not satisfied here because there is no statement after the go to. So we have only 2 leaders, the first statement and the target of the go to. So we are having prod equal to 0 as the first leader, and we will write the statements up to before 5. Statement 5 is a leader. So the first 4 statements will form block 1, and 5 is another leader. So starting from 5 up to 11. That will be the second block. And we have to draw the lines because it will go to 5. So we are going back to block 2. So hope it's clear. Basic block and flow graphs. Next we will see about the code optimization techniques that can be done on basic blocks. Basically, these transformations are nothing but code optimization techniques. So we are going to take the basic blocks, which is nothing but computation of a set of expressions, and it will be useful for optimization. So this optimization is otherwise called as transformation. So we are having 2 types: structure preserving transformation and algebraic transformation. Actually, we will study this a little more in detail in our 5th unit. So under structure preserving transformation, there are some 4 types. Very first type is common sub-expression elimination. So when we were drawing the three address code itself, we found that there are some common sub-expressions. In this first part, we can see among the four statements, uh, B plus C is common sub-expression. Similarly, A minus D is a common sub-expression. But which can we eliminate? We have to carefully analyze. See, A equal to B plus C and B equal to A minus D. So this A is being used here. And then again we are saying C equal to B plus C. So B plus C is calculated at two places. So we cannot actually consider it as a common sub-expression. Whereas here A minus D is independent. See, we are saying B equal to A minus D and then D equal to A minus D. So, or in other words, we can replace this A minus D by B because it will not accept the affect the flow of the program. So this statement alone we can change to D equal to B. So that way we are eliminating one common sub-expression A minus B. See, every computation is going to take time and cost. So by avoiding this computation, we are actually reducing the cost of the computation. So this is common sub-expression elimination. Then the second technique is dead code elimination. Now we have a statement here. If X never used again in block, then we can eliminate this statement. Or in other words, if the variable is not being used elsewhere, we can remove it. As I told you, we will study this little more in detail in our fifth unit. Then we have renaming temporary variables. See, you can see in the first part of the code, T is used 4 times. So here is T, here is also T. So what happens is if we have the same variable repeated, it might cause confusion in the memory. So whenever we have the same variable, we can always develop the good habit of having different variables. So this T is named as U. So this T is used here, so we can use here. And this T is named as V. So we are just trying to avoid confusion and memory conflicts. So this is also a structure preserving transformation. See, the structure of the code is not changed. We are just transforming it in a different code, but the original meaning and structure is not changed. The last one is interchanging statements. See, we can, this we already saw in our issues to code generator. If the statements are independent, there is no issue in interchanging the statement. So here also T1 equal to B plus C, T2 equal to X plus Y. So both are independent, so interchanging them will not have an issue. But if the statements are dependent, we cannot do that. Coming to algebraic transformations, this is something to do with the algebraic equivalent set. We have studied algebra. So the same thing applied here. We have three techniques. Basically addition of 0. See, addition of 0 is not going to have any effect. So we don't need to have this statement at all. Similarly, multiplying by 1 is not going to have an effect. It's going to give the same number. So we can avoid that. Similarly, integer exponent. See, this is a costlier statement. X to the power of 3. Instead, I can write T1, which is already x squared, into x. So multiplication is having a lesser cost when compared to exponential. So this is regarding basic blocks and flow graphs. Thank you.